Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And today, as we listen to the classic song Bad by U2, we are beginning to talk about complex numbers as 2D vectors. So let's get to it, shall we? Alrighty then. So, in chapter 6, we were talking about complex numbers in the form of a plus bi, where a is the real part of the complex number and b is the imaginary part. And we didn't have a way to represent these numbers on a plane or on any kind of graph. So we're used to the Cartesian coordinate system that used only real numbers to graph. And we are now going to be able to use a complex plane, which is called the Argon plane. And on it, the y-axis is the imaginary axis, and the x-axis is the real axis. And there's some obvious statements here that maybe you want to pause and look at, but I'm not going to spend any time reading to you because it's pretty straightforward. Now, I have included some things on vectors. So if you already know about vectors, you can skip ahead until we get back to the Argon plane because the Argon plane uses vectors. Vectors are quantities which have both magnitude, or you can think of that as force, and direction. So we got a farmer here. He's removing a fence post, and he starts by pushing on the post sideways to loosen the ground. He has a choice of how hard to push the post and in which direction. So the force he applies is a vector. Okay, so if he were to push the post with a force of 50 newtons to the northeast, you can draw a scale diagram to represent that. And here's an example of that. And if you can draw perfectly, and we say that 1 centimeter is equivalent to 10 newtons of force, draw a scale diagram. I guess the farmer was 50 newtons, but this is 40 newtons. So this would be 4 centimeters long, and it's in a northeasterly direction. Okay, so we can use vectors to represent force and direction, like a direction a plane is flying or any sort of force. Okay, so that's similar to what we're going to do here with the Argon plane. And when we do use vectors, we call this an Argon diagram. Okay, so the vector OP is equal to xy, and that represents x plus yi. So in other words, whatever the value of x is, we come over that far, and of course if it was negative we would go to the left, but we're assuming it's positive, and then up y units, and we draw from the start to the end, and we have an Argon diagram of the complex number x plus yi. For example, 2 plus 3i over 2 up 3, and we draw this vector, and we have an Argon diagram of the complex number 2 plus 3i. And you can pause and take a look at these. I will talk about negative 3i. That's a purely imaginary number, and it's just down, and it lies on the imaginary axis. So obviously, a real number would just lie on the real axis. Okay. So what does all that mean? Well, illustrate the positions of the following complex numbers on the Argon diagram. Okay. All right, so z sub 1 is equal to 3. So z sub 1 would start at the origin and just go over 3. Let's see how I do with these arrows if it goes right there. And it would like that, except it would be actually on the real axis. Sorry about the inaccuracy. Z sub 2, 4 plus 3i. So let's see how I do on this one. Okay, 1, 2, 3, 4. 1, 2, 3. See if I can nail it. Got it. That's a lot better. So that's Z2. Z3 is 5i. So that's just going to go straight up. 1, 2, 3, 4, 5. And I think you get the picture. Z sub 4, negative 4 plus 2i. So to the left 4, up 2, and that's going to be Z sub 4. Z sub 5, sorry about that. Z sub 5 is going to be negative 3 minus I. So negative 3 minus I, 1, 2, 3, minus I down there. It's always real than imaginary. Oop, I didn't change the color, that's okay. And then negative 2I is going to look like that. Okay. So what do we have? Z1 through Z6, I didn't label them, sorry. It's the pen's fault. All right. Suppose Z1 equals 3 plus I, Z2 equals 1 minus 4I. Find using both algebra and vectors, blah, 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 blah. All right, so we'll do algebra first. Okay, and if you haven't done vectors, then we'll have to do, I'll show you, give you a quick tutorial. It's not hard at all. So A, Z1 plus Z2, we should already know how to do this. This is going to be 3 plus I plus 1 minus 4I, which is going to equal, we add our real and our imaginary, that's going to be 4 minus 3I. Okay, and then B, Z1 minus Z2, Z1 minus Z2 is going to equal 3 plus I. Make sure you subtract the whole thing, minus 1 minus 4I. So that's going to be 3 minus 1 is 2. And then I minus a negative 4I is I plus 4I, or 5I. Okay. So before we do that, if I have, let's say I have the vector x and then the vector y, and I want to find vector x plus y, and I want to do it geometrically, I would redraw x, but I'm just going to leave it here. So start to finish. And then I would add y onto the end of it. Yes, so this is vector y. And what we call this is a resultant vector from start to finish is the vector x plus y. So let's take a look at that back here. Z1 plus Z2. So Z1 is the vector 3 plus I. So let me get my arrow tool. And so that's going to be 3, 1, 2, 3 plus I. That's going to go here. Okay. And then I start from here, from the end of 3 plus I, which is that. I start from here to do 1 minus 4I. So then I would go over 1, down 4. 1, 2, 3, 4. Okay. So I'm just doing this geometrically, and I'll change color here to get the resultant vector, which would go from the start to the finish. So I'm just drawing right now. Well, how did I get there? 1, 2, 3, 4. So over 4 and down 3, which would be the complex number 4 minus 3i, which is what we got here. Okay, so this is how you would do it geometrically, and this is how you would do it algebraically. Okay, so let me go ahead and do Z1 minus Z2. So again, Z1 is 3 plus I. So start here, and we get to there. So subtracting a vector is you're just going in the opposite direction. So it's going to be a minus 1 plus a 4i from this endpoint. So minus 1 plus 4, 1, oops, let's redo that, messed it up. Minus 1 plus 4, 1, 2, 3, 4. We end up there. Let me change color real quick. We'll go to red. And so I go from start to finish. And there is Z1 minus Z2. So that would be 1, 2, 1, 2, 3, 1, 2, 3, 4, 5. So that is the same as 2 plus 5i, which is what we got from the algebra. So it's the algebraic and the geometric. And if we were able to draw exactly to scale, we could represent our vectors like this. And so now, what do we do when we multiply? Well, it's it's just like the algebra. Let's just go ahead. I think we really only need to do one of these. Let's go ahead and do B. That's a bit of the more complicated one. Okay, so B, Z minus 2W algebraically is going to be equal to 1 plus 2I minus 2 times 2W, so that's minus 2 times 3, minus I, which is 1 plus 2I minus 6 plus 2I, which is negative 5 plus 4I. And if we do it geometrically, I'm going to try and do this freehand now. Z minus 2W, so Z is 1 over 1 plus 2I, so boom, right? So it would go like that. I'm going freehand instead of the arrows. And then minus 2 times 3 minus I. Well, minus 2 times 3 is minus 6. So from here, I'm going to go to the left 6. 1, 2, 3, 4, 5, 6. And then minus 2 times minus I is actually a plus 2I. So I'm going to go up 2, 1, 2. And so we would draw this vector like that. So this is actually Z. This is minus 2W. And so the result of those would simply be, I'm going to go in red from here to here, like that. Well, what is that vector? Minus 1, 2, 3, 4, 5, 1, 2, 3. Negative, 1, 2, 3, 4. 1, 2, 3, 4, because it's all the way up here. Negative 5 plus 4i. Okay. Same result geometrically as you get algebraically. All right. So to represent conjugates, we know that if Z equals X plus IY, then Z star equals X minus IY. So if OP equals the vector XY, and this is just a format for vectors, which means horizontal, and this is vertical, obviously with X and Y, vertical, then OP is equal to X minus Y. That represents Z prime. That we know, or should be obvious just from this relationship. So we'll just do these, and then you can make a conclusion yourself. 2 plus 4i, 1, 2, 1, 2, 3, 4. So it's this vector. So that's 2 plus 4i. And then 2 minus 4i, 1 over 2, down 4, 1, 2, 3, 4. So if we said this was Z and this was Z star, this is Z and this is Z star. If you do all of these, what you'll notice is that the conjugate vectors are always going to be a reflection in the real axis. Okay, like the real axis is the mirror. Negative 3i, let me do a different color. Negative 3i, boom. Positive 3i, boom. A reflection in the real axis. And then one final color, we'll go green. Negative 3, 1, 2, 3, plus 2i, that's this guy. And negative 3 minus 2i is going to be this guy. And you can see how the real axis acts as a mirror if we represent geometrically conjugate vectors. All right, so that is it. That is all I have to say. I hope you enjoyed it. I know that I did, and we will go out with more of the great U2. And with that, I am out. If I could, yes, I would.